Okay, so we are talking about longest common subsequence. So just to recap, so we have given two sequence x and y. We have given two sequence, one is of length n, another one is of length n, and we need to find a longest common subsequence between these. So for that we have simplified this problem to finding the length of the longest common subsequence, and we have defined Cij, which is basically prefixes length of the longest common subsequence of x 1 to I and y 1 to j, and we have, so this is the length of the longest common subsequence up to prefix 1 to I up to prefix 1 to j. Now, if we can find out Cij for all ij, then we are done, because Cmn length, Cmn is basically length of the longest common subsequence of x and y. Okay. So now we in the last lecture we have seen a recursive formulation for this Cij. So that is basically Cij. So that is basically Cij is Ci minus 1 j minus 1 plus 1 if xi equal to yj, and it is basically maximum of Ci minus 1 comma j comma Ci j minus 1, Ci j minus 1 where otherwise if xi is not equal to xj. And we prove this part, and to prove this part we have taken a longest common subsequence z1 to k, which is a longest common subsequence between x 1 to I comma y 1 to j, and then we have seen that any subsequence. So this is also a 1 to k minus 1 is a longest common subsequence between x 1 to I minus 1 y 1 to j minus 1. So this is one of the hallmark of dynamic programming problem. So for dynamic programming problem, basically you have two hallmarks. This is the first hallmark. So this is telling us a solution of a problem contain the solution of the sub problems. An optimal solution to a problem contain the optimal solution of the sub problem. So this is a longest common subsequence up to k. So its sub up to k minus 1 is the longest common subsequence of this. Okay, so this is a hallmark of dynamic programming problem. So let us write this dynamic programming. So programming hallmark, this is hallmark number 1. So what it is telling? It is telling the optimal substructure, the optimal substructure okay. So it is telling an optimal solution, an optimal solution to a problem contains optimal solutions to sub problems. Okay. So like if z up to k is a LCS, then any subsequence, any sub problem, any if we take z up to k minus 1, that is the optimal solution, that is the LCS of x up to n k I minus 1, y up to j minus 1. So this is one of the hallmark for dynamic programming problem. So, if we have such a hallmark, then maybe we have to be fix our mind that okay, maybe we have to go for dynamic programming approach. So, this is one of the hallmark. So, we have second hallmark also. To reach that, let us just write a algorithm for this recursive formula. So, this is the LCS algorithm. Okay, so recursive algorithm for LCS. Okay, so basically we are finding the LCS of xy ij. This is basically length of the longest common subsequence Cij. So now if xi equal to yj, then we know it is basically then it is Cij is basically LCS of length of LCS of x y I minus 1 j minus 1 plus 1. This is the this case else. So, else 2 3 else we have Cij is max of the length of these two, LCS of x y one index less and other I j minus 1. Okay. So, this is the algorithm for finding the Cij. This is the recursive call. Okay. Now what is the worst case for this algorithm? We want to analysis the worst case of this algorithm. So, when is the worst case? Worst case is worst case will happen if xi is not equal to yj, because in that case we have two call, then we have to take the maximum, and also size if xi equal to xj, then we have only one call and size is also both index reduced by 1. Okay. But if we have xi is not equal to xj, then we have to have two call, recursive call, and then we need to get the maximum of that, and even both the call we have only one index less. Okay. So, this is the worst case. Okay. So, now we will draw the worst case recursive tree for this, for some example, some values of m and n. So, let us draw the worst case recursive tree. Okay. So, suppose m is 3, n is 4, and we are in worst case. So, worst case means we have to go for xi is not equal to xj. Okay. So, we give a call with m3, m4. So, since it is worst case, we have to have two calls which one index less. So, 2 4, then 3 3, and then after calculating this C2, then we take the maximum. Okay. Again we are in worst case. So, this is index is 1 1 4 and this is 2 3. Again here 2 3 3 2. Okay. So, like this, again here 1 3 2 2, again here 1 3 2 2, like this. Okay. So, now this is common, this, and so this tree is common. So that means we have same sub problems. We have same sub problems over here. Because they are common, I mean, so unnecessarily we are doing the work double basically. So, to save that we need to memorize that, I mean whether we have calculated that, if we have calculated corresponding C1 3, then we will not calculate again for this tree. Okay. So, there are many repetition over here. So, this is the, what is the length of this, height of this tree is m plus n. Okay, this is the height of this tree. So, this is another hallmark of the dynamic programming problem. This is the many repetition of the overlapping sub problems. So, this is the repetition. So, let us write that second hallmark of dynamic programming problem. So, this is basically telling us overlapping sub problems. Okay, so dynamic programming, this is hallmark number 2. Okay, and this is telling us overlapping sub problem. Overlapping sub problems. So, what it is telling us? It is telling, so a recursive solution contain a small number of distinct sub problems repeated many times. Repeated many times. Okay. So, this is one of the hallmark for dynamic programming problem. Like if we, so we have many overlapping sub problems. So, if we have all, so that is one indication that now we must go for the dynamic programming technique. So, this is the second hallmark. So, if we see that we have some recursive formula and there we have this type of overlapping sub problems. So, many repetitions are happening, then we must be ready for, okay, now it is time for go for the dynamic programming technique. Okay. So, now let us modify that algorithm, which is a recursive algorithm, to avoid this repetition. So, that is the memoization. So, we will memorize the value which we have calculated. So, if we have calculated some value, we will memorize that, we will not recalculate again. So, that is the memoization algorithm of that finding LCS. Okay. So, let us just memoization, not memorization, memoization algorithm for finding the LCS. So, the remaining part is same, only thing, if we have already calculated some value, we will not recalculate again. So, that means if Cij is nil, that means it is not calculated, then only we go for calculating it. Yeah. So, if this, then we will go for then if, then remaining part is same. This, then Cij is basically length of xy I minus 1 j minus 1 plus 1 else Cij is basically max of these two, length of I minus 1 comma j okay. So, this part is same as earlier, only thing we have a checkpoint over here to avoid the recalculation. If we have calculated the value, we will not going to recalculate again, that is why it is memorization, we memorize that. If we once we calculate it, we will not recalculate it. Okay. So, that will give us the dynamic programming technique. So, it is basically the bottom up technique. So, it is a tabular technique. So, we will just try to find out this Cij's. So, it is basically dynamic programming approach. Okay. So, idea is basically computing the table bottom up. So, let us just take that example. So, we have the x value and y value. So, A, B, C, let us take a x sequence and y sequence D, A, B. So, this is our x sequence and we have a y sequence B, D, C, A, B, A, B, D, C, A, B, A. Okay. So, we just take this table like this. So, this is a tabular method. So, okay. So, let us okay. So, this is this we put in a table. So, this is our x sequence starting from here, this is our x sequence and this is our y sequence, and we want to calculate this Cij's. Okay. Cij's basically the bottom up way we will calculate this. Okay. So, these are all 0 because this y is not started yet and there is no common thing. So, these are all 0, these fields are all zeros. Okay. Now, we will calculate say this field. So, this is our so for this field we need to take this and this value. So, if you take this and this value, so this is basically x C11, this is basically C11, C11 is basically, so it depends on x1 y1, x1 is A, y1 is B. So, if we use the formula they are not same. So, it is basically maximum of C01 comma C10. So, these two maximum of these two, okay, these two are both 0. So, it will be 0. Okay. Now, this is basically C. So, x is 2, C2 1. Okay. Now, x2 is B, y is, so they are same. So, they are same means the formula is basically C10 plus 1. So, this plus 1. So, this will be 1 like this. Okay. So, similarly, we take these two are not same. If these two are not same, then this will be maximum of these two. So, maximum of these two is 1. Then again we have these two is same, so it will be this plus 1, so 1. Okay. So now we take these two are not same, maximum of these two is 1. Then we take these two are not same, maximum of this was 1, and we take these two are same, so it will be this plus 1, 1. Now again here, so we compare this and this, these two are not same, maximum of these two is 0, this and this, maximum of these two is 1, this and this are not same, maximum of these two is 1. So basically we are using that recursive formula. Okay, but this is the tabular method. If we have calculated that Cij, we are not recalculating again. So that is the memoization, and this is the dynamic programming technique. Okay, so now these two are also not same, so it will be maximum of these two 1. Now these two are same, so once these two are same, it will be this plus 1, so this will be 2, that recursive formula. Again these two are not same, so maximum of these two 2, these two are not same, maximum of these two 2, like this. So let us just fill it. So this not same 0, this not same 1, this same, so this is 2, these two are not same, maximum of these two 2, these two are not same, maximum these 2, these two are not same 2, these two are not same 2. Again these two, this and this is 1, they are same, this is not same, this is 1, maximum of these two is not same, maximum of these two not same, maximum of these two not same, maximum of these two, this and these are same, so it will be this plus 1, so 3, sorry, 2 plus 1, 3. Okay. So now these and these are different, so it will be maximum of these two 3. So we continue like this. So these two are not same, maximum of these two 1, these two are same, it will be 2, these two are not same, maximum of these two are same, it will be 3, these two are not same, so 3, these two are not same, again 3. Now these two are same, so it will be 4, this plus 1, it will be 4. Now again these two are same, so it will be 1, these two are not same, maximum of these two 2, not same 2, not same 3, maximum of these two 3, again these two is same, so we have these two is basically same, we have 4, and these two are not same, maximum of these two 4. This is basically our Cn comma n. This is basically the LCS of length of the LCS of x comma y for the full sequence, and this is what we are looking for. We want to find out Cmn. So this is basically Cmn. Okay, and this is the dynamic programming technique. This is the bottom up way. So if we have calculated the Cij's, we will not recalculate again. So this is a memoization. So we'll store this value and we use this value to get this thing. Okay, so this is the length of the longest common subsequence, and length of the longest common subsequence is 4 for these two sequence x and y. Okay. Now the question is, from here how we can find the longest common subsequence, because we have simplified that problem. We need to find the longest common subsequence. So we reduce the problem into to find the length of the longest common subsequence. Now you are interested, after getting the length, we are interested to find a longest common subsequence. So for that, what we need to do? We need to follow this path. So this path we need to follow. So maybe we can take this one, then we can take this one, we can take this one, and we can take this one. So this will give us what? This will give us which sequence? This will give us A, and then this will give us B, and this will give us C, and this will give us again B. So this is the longest common subsequence. Even if we follow this path, this one, even if we follow this path, this one, this one, this one and this one. So, this will give us what? This will give us this is for B and this is A and this is D and this is again B. So, this is also a longest. So, if by following this path we can get the longest common subsequence. So, we have to find a longest common subsequence. We simplify this problem to find the length of the longest common subsequence. So, by this dynamic programming method we got the length. After getting the length we just follow this path to get the longest common subsequence. So, what is the time complexity for this algorithm, for this recursive algorithm? So, basically we have a if the length of this is m, so the time complexity is, so if x is of size 1 to m and y is of size 1 to n. So, basically to compute this, the time is basically order of m into n. So, this is the time complexity for prepare the table. Okay. So, once we prepare the table we can get the length of the longest common subsequence. So, this is the dynamic programming technique and we illustrate this technique by an example which is called longest common subsequence problem. And so, for any dynamic programming technique we should have such kind of recursive formula and we should have two hallmarks. So, in the recursive formula we should have optimal substructure hallmark. So, that is telling us if we have a solution of a problem that should contain solution of the sub problems, that is the first hallmark of the dynamic programming technique, and the second hallmark is overlapping sub problems. So, if we can see the many sub problems are repeating basically, then we must think that okay, now it is time to go for dynamic programming technique. Okay, thank you.